So our isocitrate dehydrogenase. Okay, so again, what we're doing is we're taking our isocitrate, we are oxidizing it and doing an oxidative decarboxylation to give me my alpha ketoglutarate. Okay, and we're going to lose CO2. Okay, and we're going to take we're going to take oxidized NAD and reduce it to make NADH. So again, we lose a carbon here. So again, this is an oxidative decarboxylation. And what we see here is part of this reaction is non-enzymatic. So part of the reaction is non-enzymatic. Okay. And what we see here is the spontaneous decarboxylation of a beta keto acid. Okay. And not only will beta keto acids decarboxylate, but a lot of beta carbonyl type groups will decarboxylate. You can have beta diacids, for instance, will decarboxylate, and other beta carbonyl compounds. So other beta carbonyl acids. Okay. And in your organic chemistry, you see a lot of this, okay? And I'll remind you real quick of two reactions that you would see in organic chemistry, the acetoacetic ester synthesis and the malonic ester synthesis. And those are ones that involve the decarboxylation of beta keto acids. So let me just do one of those for you, so remind you of those. So malonic ester synthesis. And I'll do this rather quickly, okay? I try to go slow, but I'll try to do this one fairly quickly. Okay, so the idea here is you've got the diester, and this is diethyl malonate, so it's the diester of malonic acid, so diethyl malonate. These protons here are alpha to the carbonyls on both sides, so they're extremely acidic. Okay, so you treat this with a base to remove those alpha protons, and then you alkylate. Okay, so typically what you do is if this is the ethyl ester, you would use ethoxide, and then you would alkylate, and this has got to be a primary alkyl halide. So you make the enolate, and you do this. Okay, and so now, okay, you have now put an alkyl group on here. All right. So you can actually do this twice. You can put two alkyl groups on here. You can actually use a substrate here that has two halides on it, a dihalide, and make a cyclic ring here. And when you hydrolyze these esters, you're going to end up with your beta diacid, okay? So let me hydrolyze these esters. All right, so let me do the beta diacid. And let me put my OH on this side. I really still messed that up. I want to put my OH on this side. There we go. Okay, if I didn't confuse you, I hydrolyzed this ester to that acid. I hydrolyzed this ester to that acid, and I'm showing this proton specifically on that carboxylic acid because I'm going to do something with that proton. So this gives me a beta diacid. And these will spontaneously decarboxylate as well. All right, so the way you can visualize this is you're going to just make an enol. So I bring this electron pair in. This electron pair comes in here, and this electron pair picks up that proton, and I make an enol. So here is my carbon dioxide. Okay, here is my essentially enol, and then this will tautomerize. You know, it's just so unnatural for me to show a bond to a hydrogen. Okay, so again, this is your enol, which will tautomerize. So this electron pair comes in, and this electron pair picks up that proton. Okay, and so now it has again, lost carbon dioxide, and now I'll have as my product there's my acid. Okay, here is my alkyl group that I have added. Okay, so again, let me do this for you. There's your alkyl group that you've added. Okay, here's the alkyl group that we've added. So this is from the malonic ester. Okay. All right, so in essence, what you see in your organic text, okay, so the whole point of this was this is the spontaneous decarboxylation of a beta diacid. Okay, so what you see in organic textbooks basically is this is your alkyl halide. You use the malonic ester, and again, they will abbreviate this different ways. I'm going to write out the structure, okay? Some textbooks will abbreviate this in some crazy ways. Okay, so there's my malonic ester, and I'm going to use, again, the ethoxide, and the net is, oh, then you do the hydrolysis. You have to heat this up to do the hydrolysis of the ester. So the net is that you've added this alkyl group to 2 carbons. Okay, so, oh, just trying to show that that's primary. That's the only reason for showing that carbon is that must be primary because it's SN2. All right, so again, in essence, what you're doing here is you're converting a primary alkyl halide to a carboxylic acid with 2 more carbons. So the malonic ester synthesis, again, converts a primary alkyl halide to a carboxylic acid with 2 more carbons. Okay. All right, so if you do the malonic ester synthesis, we also do the acetoacetic ester synthesis. Okay. And again, a review of organic acetoacetic ester. This comes from the Claisen ester condensation. And what you've got here is your acetoacetic ester. So, excuse me, this is your acetoacetate, and this is your ethyl ester. So this is ethyl acetoacetate, so or the acetoacetic ester synthesis. And what you're going to do here is you're going to add essentially you're going to convert your primary alkyl halide into a methyl ketone with 3 more carbons. So when we get to the end, that's the net. You're going to take your your primary alkyl halide and run it through this synthesis, and you're going to get a methyl ketone with 3 more carbons added to this. All right, so on the acetic ester synthesis, again, you're going to use, if this is a methyl ester, you would use methoxide. Okay, that's going to again make the enolate. I'm going to go ahead and cheat and make that. Okay, there's my enolate. This is obviously alpha to the ester and alpha to the carbonyl, so these protons are highly acidic. And then I'm going to react this. This must be a primary alkyl halide because you're going to do SN2. Okay. And again, you can do this twice in this synthesis, just like you can up here. You could add another alkyl group on here. All right, so again, this is the alkylation step. And again, I'm showing another carbon there just to show that it must be primary. You don't necessarily have to do that. Okay, and now we're going to hydrolyze this. So do the hydrolysis and heat. Okay, and you hydrolyze that to the beta keto acid. So here I have instead of a beta diacid, I've got a beta keto acid. Oh, I'm sorry, I didn't really do this too correct up here. Okay, just doing hydrolysis, converting the esters to acids. Okay, so here I've converted the ester to the acid. And the same thing, I got a beta keto acid. And I'm going to redraw this where I have the OH on the right side so I can pick it off by the carbonyl. Okay, so again, your beta keto acid is going to spontaneously decarboxylate. Okay, so I'm going to lose this carbon dioxide. And so in the overall reaction here, okay, well, I'm going to redraw that so you can see the mechanism. So all I'm going to do is redraw the acid to the other side so I can get that proton. So I've just changed the conformation. Okay, I rotated this around, so I got the OH over here. And now this is my acid functional group. This is the alpha carbon, this is the beta carbon, so I got a beta keto acid. So alpha to this carbonyl, beta to that carbonyl. So I have a beta keto acid. All right, so again, if this is going to spontaneously decarboxylate, I bring in this electron pair to make my carbon dioxide. This electron pair has to go somewhere. It's going to go right here, and then this is going to pick up the proton. Okay, so now, again, I'm trying to draw all this stuff in the same orientation. My double bond is there. I have my enol. And the enol will tautomerize to the ketone. So tautomerization. And so now just simply bring this electron pair back in, pick up that proton. And so now I would have okay, and so in essence, the net was that I've added 1, 2, 3 carbons to my primary alkyl halide in the form of a methyl ketone. Okay, so the acetoacetic ester synthesis again, converts a primary alkyl halide to a methyl ketone with 3 more carbons. Okay, so if you're studying organic chemistry and reactions in organic chemistry and learn synthesis, these are 2 very important ones, and these are the nets that you get for the acetoacetic ester synthesis and the malonic ester synthesis. And draw correctly is this, okay? This should be a tautomerization. So again, if I'm looking at this, this is your alkyl halide. So from your primary alkyl halide, and this fragment, your 3 carbons, is from your acetoacetic ester. So 1, 2, 3 carbons from your acetoacetic. Okay, so you got the malonic ester synthesis and the acetoacetic ester synthesis. And again, that was a long way to go to make sure that you understand what? Beta keto acids will spontaneously decarboxylate. Beta diacids spontaneously decarboxylate. Any beta carbonyl acid is going to spontaneously decarboxylate. Okay, again, if you're in organic chemistry, you're looking at aldehydes, ketones, esters, even nitriles here, all kinds of groups. Protons alpha to those groups are going to be acidic. If they're alpha to 2 of those groups, they're even more acidic. All right, so what are we going to do here? A long way to go. We're going to take that secondary alcohol of my isocitrate and oxidize it to a ketone, and it's going to yield a beta keto acid that is going to spontaneously decarboxylate, and hopefully I can squeeze that in. My isocitrate dehydrogenase. Okay, so again, here is my isocitrate. Okay, now, again, normally we don't think of removing hydrides, but that's essentially what we're doing here. And how are we removing that hydride? Well, we got NAD that's going to accept it. So I'm going to draw my NAD here. And I'm just going to draw the business end of the molecule. So there's my plus charge on my NAD plus. Okay, and again, I said it many times, it's just unnatural to draw a bond to hydrogen. All right, so I'm going to remove that hydrogen, bring in an electron pair, and this hydrogen with its electrons is going to leave as hydride. Okay, so I'm doing a hydride transfer. So the NAD plus is positioned where it's ready to accept that. Okay, so now I'm going to have a double bond here. Oh, I left out a carbon. Oh my gosh. Sorry. Okay. So again, this is from the acetyl-CoA. This arm is from your oxaloacetate. 1, 2, 3, 4 carbons from the oxaloacetate, the 2 from the acetyl-CoA. All right, so this gives me what? 1, 2, 3, 4 carbons is the 4-carbon dicarboxylic acid succinate, and this is the oxalo group, so oxalosuccinate. And put it in brackets because it is, again, an intermediate. It stays on the enzyme. And again, it's the next step is our non-enzymatic step. So plus my NADH. Again, we're not specifying on our dehydrogenases whether that hydride attaches from the front or the back, and that's how we distinguish between dehydrogenases, okay, and the different types, but we're not doing that in this class. But again, your hydride transfer goes to the number 4 position, okay, and I didn't quite finish the movement of the electrons here. That goes to the nitrogen, and we lose our positive charge for our NADH. Now our oxalosuccinate, this is our beta keto acid that will spontaneously decarboxylate. Okay. And again, let me redraw that. I'm going to have to pick up a proton from the media. Okay, because in organic class we draw everything protonated, all right, but in here we draw everything dissociated, okay, with the negative charges. Of course, if you're in organic class, you'd make those all carboxylic acids with the proton. All right, so this is my beta keto acid. I'm going to bring this electron pair in. Okay, and just like we did in our examples a moment ago, we're going to make an enol. So here's where I'm going to pick up a proton. Okay, so I have a proton that I pick up, and this is going to make, again, my carbon dioxide. Here is my enol. So there's my carbon dioxide, and again, so I bring this electron pair in and bring this pair out to pick up the proton. So this is my tautomerization. Of the enol to the keto form. And so this is going to give me my product. So 1, 2, 3, 4, 5 carbons with a ketone at the alpha position, alpha keto glutarate. Glutarate with an R, not an M, okay? All right, so again, this is my oxalosuccinate. It spontaneously decarboxylates to give me my alpha KG, my alpha keto glutarate. Thank you.